Dear student, this is the time to check it our answer what we have done in our examination, right? In class 12, okay? So in our chemistry, there are 4 different types of the questions given, right? The first question is based on a very short answer type carrying 1 mark, and there are 10 questions, and there are 4 questions for objective multiple choice question. Then there are 1 2 3 4 5 6 7 8 9 10. So 10 questions, for the short answer type 2, so carrying the 2 marks. And there are 1 2 3 4 5 6 7, so 7 questions of the short answer type 1 carrying the 3 marks, and the 3 more questions for essay type question carrying the 5 marks. So in my previous video we already discussed about the keys of the essay type questions. I hope you checked your answer with my keys given to you. Today let me start to check our answer from the very short answer type questions carrying 1 mark. Questions carrying 1 mark, it's normally based on your knowledge, understanding and the concept, right? Some of the questions are level of the difficulty, somehow difficult, and some of the questions could be answered very easily, some normal students, right? So let me analyze the question by question. So you pick up the question, just you take out your question paper which is already written in your exam, and let's see how was your answer. Are you ready? So let me read the question number 1. Suggest a liquid that could be added to water so that the mixture boils below 100 degrees Celsius at the same pressure. Get it 1 mark. So this is question from the solution. Now here in our solution, so this is the solution of the liquid and liquid, alright? So liquid solution. Here this mixture of the liquid boil at one particular temperature. That liquid mixture we call azeotropic mixture. So different liquids having a different boiling point when we mix together, so that mixtures boil at one particular temperature. That mixture we call azeotropic mixture. So there are 2 different azeotropic mixture. One is so the mixtures boil above the temperature, above the boiling point of the one of the liquid, so that we call maximum boiling azeotrope. Then another type of the mixtures of the liquids boil below the boiling point of the one of the liquids given here, that is the minimum boiling azeotrope. Now here that question is related to minimum boiling azeotrope. So the question is given here. So when you see the textbook, so examples are given here, right? So I just give you the example of the maximum boiling point. You can take the water, one of the component here. So under liquid you can take the nitric acid. That mixtures boil above the boiling point of the water. That is what we call maximum boiling azeotrope example. So our answer is the minimum boiling azeotrope. What is the example here? One of the mixture, one of the component is water. What is the temperature? 100 degrees Celsius. So what will be our liquid we can suggest here? So many liquids are here along with our water. So the very common and a very easy liquid, which can remember that liquid, which get the liquid, the boiling point of such a liquid is lesser than the boiling point of the water. So that is the example we can write ethyl alcohol. So you can choose the answer is the ethyl alcohol, right? So this is the answer for that question. You can choose the ethyl alcohol, not exactly the ethyl alcohol. Somebody they may write another types of the alcohol, but I suggest you ethyl alcohol is the most suitable answer for that question. Okay. The second question, that is, okay, let me read, just see your question. A solution of magnesium sulfate is electrolyzed to carry out a deposition of 24.3 gram of magnesium at the cathode. How many electrons pass through the solution during the process, right? Okay, so this is the question number 2. Now here, so from which part of the chemistry topic? So this question arises. I think this is from the electrochemistry. Right, in our electrochemistry we have two different types of the portion. We just discussed it separately. So one is the electrolytic cell, another is the electrochemical cell. So this is the question from the electrolytic cell. So the name of the process, okay, in our electrolytic cell, that is the electrolysis. So this is the electrolysis of the magnesium sulfate. So before the electrolysis started, this magnesium sulfate dissociated into the magnesium ion. So magnesium ion is Mg2 plus sulfate ion SO42 minus, right? And during electrolysis, so there are two different electrode reactions. One at the cathode, another is the anode. So the positive charge carry this, okay? So it's okay, take the reactions at the cathode. So question is the cathode. So now we are going to write a magnesium 2 plus. So this magnesium 2 plus, okay, during the electrolysis, right? So that means when we pass in the electricity, so from the electricity we receive the electrons, okay? So how many electrons we receive to convert this magnesium 2 plus into the magnesium metal, that is the solid, deposited at the cathode? How many electrons require? 2 electrons. So this number of electrons we write in the terms of the mole. How many moles of the electrons? 2 moles. We remember it, right? So when we pass in the 2 mole of the electrons, okay, so how much magnesium deposit in terms of the mole? That is the 1 mole of the magnesium sulfate. So the mass of 1 mole of the magnesium, that is equivalent to the atomic mass. Atomic mass of the magnesium, we all remember that 24 grams per mole approximately. Now here, so this much we write it. Now again, so in the questions here, see, let me write this 24 gram. In order to deposit 24 gram of the magnesium, how many moles of the electron? 2 moles. This number of the electrons in terms of the moles, we convert it into the number. So you remember the mole concept? By mole concept, we are going to find out the numbers, right? So I think you remember that. How many number of electrons in 1 mole? In 1 mole, how many electrons? It should be the 6.023 into 10 to the power 23 number of electrons. So here from that mole concept, how many moles of the electron? Here 2 moles. That means, so in terms of the number of the electrons, so 2 into 6.023 into 10 to the power 23 number of electrons. So if we pass in the 2 into 6.023 into 10 to the power 23 electrons, how much of magnesium deposit? 24 gram. See, look at the question. Here the same gram of the magnesium, same, approximately same, 24.3, that is equal to 24, right? So we can consider 24. So in order to deposit 24.3 grams of the magnesium, how many electrons can be passing? That will be the answer here, 12.0K26 into 10 to the power 23 electrons. This is the number of electron passing. This will be the answer, right? Okay. So I hope you wrote in your answer paper. So this answer. So if you write a 12.026 into 10 to the power 23 electron, that's okay. Or if you can write a 1.2026 into 10 to the power 24 electrons can also be right. So that only we change the exponential power, right? So we can write either 12.02 into 10 to the power 23 or 1.2 into 10 to the power 24 electrons. So this is the answer of this second question, right? So I consider this question is not much difficulty. So only based on the understanding, right? Okay, question number 3. Cyclopropane undergo isomerization at 1000 degrees Celsius to propylene following first order kinetics. Okay, so the rate constant value is given here, 9.9 per second. How long would it take for the concentration of cyclopropane to decrease to 50% of its initial value? So this question number 3, from which chapter? That is the chemical kinetics. So this question also based on your understanding, right? Okay, now here, so what type of the order of the kinetics follow this reaction? That is the first order. First order kinetics. Okay, now so rate constant value is given here. K is the value, rate constant 9.9 per second. So rate constant value is given. So how long would it take for the concentration of cyclopropane to decrease the 50% of its initial value? That means half of the K initial value K decrease. How long it will take? So what it does mean? So that is what we call half-life period. Okay, so now the half-life period, the question is here. So for the first order kinetics, what is the half-life period as your mathematical equation? What is the half-life period? So for the first order reaction, half-life period equal to 0.693 divided by K. So this was our mathematical equation we expressed. Now here, K value is given here. So we are going to find out the half-life period. What will be the answer here? 0.693 divided by K value is 9.9. This is the per second. So what will be the answer? When you divide this, I think you will find 0.07 second. This is the answer of the third question. I think I don't consider this is the difficult question. This is the easy question. It's based on your understanding, right? Next, question number 4. Go to the question number 4. So, what is pyrometallurgy? In our chemistry, a very small portion, very small chapter, okay, that is what we call metallurgy. It's carried only 3 marks, okay, from that chapter. So this is the question related to metallurgy. Here, let we start to remember that what do you mean by metallurgy? We know very easy that extraction. This is the process of extraction of the metal from their ore, from its ore, right? That is what we call the metallurgy. So in prefix, if they write a pyro, right, what it means that it related to the temperature, right? So when we define the pyrometallurgy, so what it does mean, so the process of the extraction of the metal from its ore at higher temperature. At higher temperature. So this is the answer of this question, right? So as I just give you some extra idea about it is that, right? So as an example, extraction of the iron from the iron ore in blast furnace. Blast furnace is the different temperature ranges. In the different temperature ranges, so we extract the metal, okay, from each ore, right? So this is the answer of the question, right? Then question number 5. Why do actinoids show larger number of the oxidation state as compared to the lanthanoids, right? Oxidation stage. Okay. So here question is, why do actinoids show larger number of oxidation state? See, when we study about the D block elements, so this okay, actinoids and lanthanoids are F block elements. Right? When we study about the D block elements shows the variable oxidation, means so many oxidation states here. Why? So here in the D block elements, I hope you remember that D block elements. So oxidation number is the number of electrons which are contributed in the formation of the bonds. Understand? So how the electrons are contributed in the formation of the bonds? So the electrons present in the outermost shell, that electrons are responsible to formation of the bonds here in D block elements, right? So what is the outermost electronic configuration? We know n-1, D1 to 10, then ns2, right? So here the energy between the D and S orbital, if this energy difference between the D or D and S orbitals are larger, so these electrons cannot be contributed in the formation of the bond. So D block element shows the variable oxidation state because these S orbital and D orbital energies are comparatively very closer, very close. Therefore all these electrons are contributed in the formation of the bond. Similarly in the F block elements, what is the outermost electronic configuration is n-2, F1 to 14, then n-1, D0 to 1, then ns2. Now here, so these electrons present in the S, present in the D, present in the F, so these electrons can be contributed in the formation of the bond. If all these electrons are contributed in the formation of the bond, so that F block elements shows the variable oxidation state. Why? The answer is, as I already mentioned that, so energies of S, D and F orbitals are comparatively very close. So therefore all these electrons present in the S, D and F are contributed in the formation of the bond. This is the answer of the your question. We go to the question number 6. This question number 6 is related to organic chemistry. In your organic chemistry, the first chapter is haloalkane and haloarenes. So this is the question related to haloalkanes and haloarenes. So question number 6. This is question from haloalkanes. Now, what knowledge related to this haloalkane. So here, isomeric monochloroderivatives, how many, right, will be formed when 2-methylpropane is subject to photochlorination. So this is the preparation of haloalkane. Preparation. So what type of the preparation? So preparation of haloalkane from the alkane, right? So from the alkane, so what is the method we apply? Direct halogenation. So under what condition? So condition applied here, sunlight. So by using the sunlight, under the sunlight, so alkane can undergo halogenation, right? So that reaction what we call photo. So this halogenation what we are going to do here, that is the chlorination. So that is the photochlorination. So that means, so from the alkane, hydrogen can be replaced by the chlorine under the sunlight. That is what we call photochlorination, right? Monochloro. That means only one chlorine replaces the one hydrogen here, right? So what the knowledge we understand? What the knowledge we should understand that, so how many hydrogen can be replaced by the chlorine, right? So the hydrogen present in our given alkanes may be same, maybe equivalent or may not be equivalent. The environments may be different. So let me write the our alkane. What is the name of the alkanes given? 2-methylpropane. Propane means 3 carbon, right? And it should be single bond, right? Then 2-methyl means added 2 methyl is there. Then let me complete the hydrogen. So how many hydrogen will be here? 3 hydrogen. Here also be 3 hydrogen. So in order to satisfy the 4 bonds, so 1 hydrogen should be right here. Right. See. How many hydrogen here? 3 hydrogen. Here also 3 hydrogen, 3 hydrogen, and this 1 hydrogen here. At this carbon, how many carbons are bonded? 3 carbons. Then now, the question is, what are the foreign properties of the hydrogen bonded at a different carbon? See, if these carbons are bonded at a particular carbon, these carbons are same, right? That means the hydrogens present at all these 3 carbons are equivalent. That means, the equivalent hydrogens are here 3, here 3, here 3, right? That means all these 3 hydrogens are same. Then another hydrogen is present at this carbon, right? This hydrogen present at this carbon is not the same with this hydrogen. So this is the another hydrogen. I mark it here. So these hydrogens are same. That means what we counted, the number of the hydrogen is 9, but all these 9 hydrogens are same. Now, when these compounds undergo the chlorination, chlorine under the sunlight, right? So only 1 hydrogen means only 1 chlorine replaces the 1 hydrogen, right? So how many hydrogen can be replaced, right? So here, this chlorine can replace this hydrogen, this chlorine can also replace this hydrogen, this chlorine can replace this hydrogen. The hydrogens replaced from these 3 CH3 group are all same because they all are equivalent. That means 1 hydrogen can be replaced from these 3. That means 1. Right? So we found 1 isomer of the monochloroderivatives. Then another. When this chlorine replaces this hydrogen, we found 1 isomer, not 9, because all these 9 are equivalent. Therefore, so we write 1 plus. If this chlorine replaces this hydrogen, because these hydrogens are different from these hydrogens, therefore the hydrogen replaced by this chlorine, we found another isomeric one. So altogether, how many isomeric monochloro derivatives we found? That is the 2. Answer should be the 2. Understand? So answer will be 2. Okay. So I hope you just check it your answer. So somebody may write 3, somebody may write 4, somebody may write without some lacking of your understanding, right? So due to some lack of the understanding, so they may have some difficulty to write this number correctly, right? So when we explain during the class, your teachers may forget to mention the types of the hydrogens present in our alkanes given, right? The question number 7. This also related to our haloalkanes. So this is from the haloarenes. Question number 7 from the haloarenes. Now here, so this is the iodination, same as the chlorination, right? So this is the iodination of benzene. So here that is the preparation of iodobenzene. So how iodobenzene prepare from the benzene? So that is the one of the method is the iodination. How do we write the reaction? This is the benzene, one of the hydrogen here I write. So here also one hydrogen, here also one hydrogen, one of the hydrogen I write separately. So it reacts with iodine. So this reactions not takes place easily. Number 1, remember, right? This reaction does not take place very easily. So the reaction is reversible, right? Okay. In order to form this iodobenzene, means this one of the iodine replace this hydrogen. So this hydrogen should be removed. Okay. So in order to remove this hydrogen by the iodine, so there is the condition. But in some cases of the chlorobenzene or bromobenzene, so they don't use any catalyst. But in this case, they use the catalyst. That is what we call oxidizing agent. What is oxidizing agent? That is the nitric acid can be used. So that is the oxidizing agent can be used in this reaction. What is the role of this oxidizing agent? Here, very important role. So this is NO3 playing here, right? What is this? Here, without removing this, so this hydrogen when we remove there, so this iodine, one of the iodine, so here is the 2 iodine, so one of the iodine it could be replaced here, so that will be the I plus and another will be I minus, right? So here this I minus, so replace this H plus, so now what will be the product? H I. So what will be this? This is the minus, right? So this is the iodine, so here what is the iodine here? So this iodine 0, this iodine 0, oxidation number is 0, that another iodine is I minus. What is the reaction here? So this reaction is 0 to minus, that means it's from that. So what will we doing here? That plus 1 electron, that is the reduction, right? So this iodine is reduced to I minus. So this is the oxidizing agent. So here, so this I2, so that means converted to this hydrogen iodide, that means this has NO3, so here oxidize to HI. This is the role of the HNO3. So when you write answer that, what is the answer that? This HNO3 oxidized to HI. That is the answer of your Okay, question. Okay, next question, number 8. Question number 8. So why is orthochlorophenol more acidic than phenol? So this is also questions based on your understanding. So this is the question from the phenol. Remember, okay, when we study about the chemical properties of the phenol, so we study about their acidic nature. Okay, so phenols are acidic in nature. Okay, how can we represent it? So phenol, what is the structure? So from the phenol, okay, the hydrogen is present here, so it's liberated as H plus. So it formed the phenoxide ion. So comparing the stability of this phenoxide ion and phenol, so phenoxide ion is more stable than the phenol. This is more stable. To stabilize this phenoxide ion, right? Okay, so there is some substituents. There is some substituents. It can be bonded at the ortho position, it can be bonded at the para position, it can be bonded at the meta position. So here is the, okay, our ortho position. Here is the group. Okay, the group present at the ortho position. Okay, so this group what we call the substituents. What is the effect of these substituents on their strength of the acidity, strength of the acidic, okay, I mean acidic strength of the phenol, right? So here there are two different types of the substituents. One is the electron withdrawing group, another is the electron donating group. Now in the question is orthochlorophenol. This is the orthochlorophenol. Now here, so let me find out here what is the type of these substituents, right? So we consider this chlorine is the electron withdrawing group. Number one answer is, since chlorine is the electron withdrawing group, answer is since chlorine is electron withdrawing group. So what is the role of this? Withdraw electrons, right? So this chlorine withdraw the electrons, okay, towards the chlorine atoms. Okay, what will do? Stabilize the phenoxide ion. Okay, so stabilize the phenoxide ion. Okay, disperse the negative charge. Okay, disperse the negative charge. Okay, and stabilize the phenoxide ion. Okay, is to release, okay, hydrogen ion, okay, and thus okay, orthochlorophenol more acidic than phenol. Thus ochlorophenol, okay, more acidic than phenol. This is the answer. Right, so this is your answer. Okay, so as I added to your idea, okay, so if this substitutes electron withdrawing groups, so the acidic strength will be increased. If the substituent is electron donating group, the acidity will be decreases. Okay, so that's the part of your idea what you have learned during the classes, right? What about question number 9? So basically most of the questions are based on your understanding. So we have to go through the questions very carefully because this is the questions related to your understanding and it depends upon the your how you seriously studied your books. Okay, mostly the questions are related to the your the textbook. Okay, now here the question is given here. An amine with the molecular formula amines. This is the question number 9. Amine. It's very easy to given here amine. Okay, the molecular formula is C3H9 and nitrogen here. So here reacts with nitrous acid HCl. So why I write a 3? Because we are going to write it okay different. Now here, so we have a different isomers of this amine, right? So add the nitrogen here. Okay, add the nitrogen. How many bonds will be here? 3 bonds. Okay, now here add the nitrogen. If one carbon is directly bonded to the nitrogen, right, and 2 hydrogens bonded to this nitrogen, these types of the amine we call primary amine, right? So how many carbons? There 3 carbons. So the rest of the carbon it should be bonded with the carbon. How many? 3, 2, 2. So 3, 2, 5, 7, 8, 9. So this is the 3 carbon, is 9 and 1 nitrogen. If we draw like this is the primary amine. Understand? Another one, if this nitrogen bonded with the 2 carbons, right? And one of the bond is bonded with the hydrogen, right? So if this nitrogen is bonded with the 2 carbon directly, okay, that types of the amine we call secondary amine. And how many carbon here? 3 carbon. So the remaining carbon it can be bonded here or it can be bonded here. So let me complete the hydrogen. 3 hydrogen, here will be 2 hydrogen, here will be 3 hydrogen, then. So 3 plus 2, the 3 plus 6 plus 2 is 8, 9. Same number of this hydrogen. So these types of the amine what we call secondary amine. Okay. The number 3 is at this nitrogen the remaining the 3 bonds is bonded with the 3 carbons, right? So no more hydrogen because it should be the 3 bonds should be nitrogen, right? So how many hydrogen will be here? 3. So the carbon, I mean the nitrogen which bonded with the 3 carbons directly, that is types of the amine what we call tertiary amine, right? So the questions given here nitrogen. So question number 9. What should be right the answer? So you just find out which one will be right in your answer paper. So this amine may be primary or maybe secondary or maybe tertiary. If these amines undergo this reaction, right? So if this compound, this amine is primary, what would be the compound? What would be the product? That should be the diazonium, right? Here diazonium chloride should be formed here. Okay. What will be the compound here? That will be the CH2. So these types of the compounds, okay, if this compound is formed, right, so that compound should be the primary amine. But in the question is nitrosamine, okay. So what will be the product of nitrosamine? This is the nitrogen, then here, okay, it should be double bond, then nitrogen, here will be the single bond, it should be double bond, oxygen. So here it should be. So this compound is what we call a nitrosamine, okay. So the remaining these 2 bonds, it should be the CH3, CH2, CH3. So this compound, if this compound is formed, what will be the name of the compound? What will be the amine? This should be secondary amine. So in the questions given here, nitrosamine derivative. So this is the nitrosamine, right? So if the compound, if the product is nitrosamine, what will be the name of the amine? What will be the amine? That will be secondary amine. So we have to draw this answer, right? The structure of the amine, what we have to draw? We have to draw this one. This is the answer of this question number 9. So this question, I think is just directly copied from your textbook. Okay, so those who are seriously go through the books, so I think they could answer very easily. Then now question number 10 is little bit very confusing, right? So this is question from the polymer. Now in our polymers, we have two different types of just polymers based on the number of the or types of the our monomers, right? So one is homopolymer. Homopolymer means the same types of monomer, right? Same types, okay? No different types of the monomer. If we have the same types of the monomer from polymers, that types of the polymers we call homopolymers, okay? Then number 2, different types of the polymers, different types of the monomers polymerized to form the polymers, that what we call copolymer. Now in the question is the copolymer, right? So what are the monomers? One is the isoprene, another is the propene. Okay, so it does not mean that, so what will be the name of the polymer, because it may be, so that is not a question for you, but the question is predict the magnitude of the intermolecular force present in the polymers. See, in the copolymers, okay, remember how it does form, okay. So let me write, this is the A, that is the one of the monomer. So it should be different with the another monomer, B. Suppose this is the one monomer, this is another monomer. So it's polymerized, form the very long chain of like that, right? So now in copolymers, different types of the copolymers form, right? So in between the polymers, okay, some are crossing, some are very simple chains. So in order to form the chain, so if the polymers form, see, this is the isoprene and propene, very small monomers. If they are polymerized, okay, in between them there will be the intermolecular force of attraction, right? So this polymer, okay, the magnitude of intermolecular force present in this polymer, if there is the very strong, so that will be very hard. If there is a very weak, there will be very soft, right? So the copolymer formed by the isoprene and propene, that will be very strong, very hard, right? Therefore, their magnitude of the intermolecular force present in the polymer will be stronger, right? So that will be the answer, stronger. So this is my observation. What will you write? So that means, so this question somehow confusion. So some bodies they have some confusion to write it. So only though we have to write it, the stronger. Okay. That means the intermolecular force present in the polymers can increase with increase the our monomers, right? So that is the answer. So now this much is the very short answer type question. So as I already told you, so these questions are based on your understanding. So not only our knowledge requires, so when we study, so we must remember that we should understand what are written or what are teach you by your teacher. So and at the same, so you please remember that when you write your exam, you read the question very carefully, right? Okay, now come to the MCQ question, multiple choice question, right? Okay, so here So this multiple choice question here, so the question is related to electrochemistry. This is also from the electrochemistry, and this is the direct question from your textbooks given there. Okay, so here, so fuel cell. So in our fuel cell, there are two different types of the reaction takes place at a two different electrode. So in the cell, we have a two different electrode. One is the cathode, one is the anode, right? So questions given here. So we have to choose there. Okay, what is the reaction takes place at a cathode? When we check it in your books, right? So there is no any matching of these reactions found. I think so there is some mistake in the question paper, right? So but as I observe the answer, so the answer A is the most suitable answer for that, okay, for this question. But instead to write here, so this option number A, O2 should be there, then 4 His plus should be there, then 4 electrons should be there. So at the cathode, so it's very easy to understand that for at the cathode there will be the reaction, reduction reaction number 1. Okay, so reduction reaction, okay, so takes place at the cathode, right? Reduction means addition of the electron. So here addition of electron number 1. So what is the product here? 2H2O. So whether this product may be correct or may be wrong, that is up to the okay, question setter who are setting. So this should be the 4OH minus, this should be, right? So here instead to write a 2H2O, it should be 4OH minus. So that will be written in the book. So we can compare to what will be the option. But anyway, but option number B, there is the loss of electrons written on the right side. So that is the oxidation. So oxidation does not take place at the cathode. So option number B is not correct, not matching. Option number C also written no electrons on the right side, that is oxidation, that is not matching. Then option number D is the redox reaction. So redox reaction does not take place at the cathode. Redox reaction is the reaction, final reaction. After the case complete the reaction, I mean the from the cathode from the anode, the addition of these two reactions, it's found redox reaction. So the D is not a correct answer. So but whether the question, whether these reactions may be correct or may be wrong, but I observed that from the certain things, so we found that so cathode should be reduction number 1, no doubt, right? Reduction should be right addition of the electron. We add it here, so we found it. So basically we find that the answer A is the correct option, right? Then question number 12. What is the multiple choice question? Question number 12. Question number 12 is which of the following lanthanoid ion in solution is a good oxidizing agent, right? So look at number A. So I don't remember what is the name of the element, but I could observe my chemistry here, very easy. Right, now here. So lanthanoids, okay, what are the oxidation state, right? So +2 oxidation state is possible, +3 oxidation state is possible, and the maximum is +4 oxidation state. The lowest one is the +2, the highest one is the +4, in middle that is the +3. So +3 is the most stable oxidation state of our lanthanoids. Remember, most stable. Here, so if the oxidation number increase means +2 to +3, Okay, what is the name of the reaction? Oxidation. Alright. So if the oxidation number increase +2 to +3, what is the reaction? Oxidation reaction. Those species undergo the oxidation reaction, that species, okay, what we call reducing agent. Okay, so here lanthanoids, okay, what ions carried a +2 are strong reducing agent. Understand? Then number 2, this +4, what is the possible that is can be reduced to +2 or +3, right? But the most stable is the +3. So this +4 is possible to reduce to, okay, +3. Okay, so what is the reaction? That is the reduction. Reduction means the, okay, decrease the oxidation number. So +4 can be reduced, right? So those species which undergo the reduction, what is it? Oxidizing agent, right? So in the given question, right, all these three are 2 plus, that means +2. That means all these three are +2 oxidation state. All these three are what are belonging or reducing agent. So here this +4, so only the +4 can be reduced, that means oxidizing agent. Therefore the correct answer is D. So easy. See here 3, this +2, this +2, this +2, so +4 is only the odd one, so it can be found out very easily. So plus D, this answer, right? Question number 13. Alright, which of the following is a heterolactic complex? So it's not much a difficulty and not much easier, but it's teachers not much serious to talk, to teach about the, okay, heterolactic complex. Okay, another is the homolactic, another is homolactic. So this question from the coordination chemistry. So in our coordination chemistry, we are talking about the coordination compound or complex compound. Now here, when we write the quick complex compound, we use the square bracket. So the things what we write inside the square bracket, what we call this is the coordination sphere or coordination entity. Right. So in the coordination spheres, okay, what are the spaces given? What are the spaces there? So metal should be there, okay, then ligand should be there. How many ligands should be there? Okay, it depends upon their coordination number, right? At the end. So, but when we are talking about ligands, right? So, depending upon the different or, okay, different types of the ligands written in the, okay, written within the coordination sphere, we divide it into two types of the, okay, complexes. One is homolactic, another is heterolactic. See, homo and hetero, so it's the very simple meaning is that what I mentioned it, understanding. Homo means same, hetero means different. Okay, very easy to find. Okay, so within the coordination spheres, okay, if we have the same types of the ligands present, that types of the complex what we call homolactic. If you find different types of the ligands within the coordination sphere, that is the heterolactic, okay, complex. See, look at in the option number A. So inside the coordination sphere, the ligand is Cn. Only one Cn. That means only one type of the ligand is written there. In the question option number B, within the coordination sphere, only one type of the ligand, that is NH3. And option number C, there are two different, okay, ligands. One is NH3, another is Cl2. CN. But in option D, only one type of the ligand, that is H2O. So what will be our answer? Answer is C. Right? Okay. Option number C is correct answer. So that's also based on your understanding. Question number 14. This MCQ, okay, Williamson's method. Okay, sometimes we call Williamson synthesis. So this is a useful method for the preparation of the ether. It's very clearly mentioned what we understand that. Okay, however, it will not be work in the preparation of this. See, they are all the ethers. One ether, number A. So I write very clearly this one. Okay, this and this one is the same, right? And these are the aliphatic, what we consider here, right? So if these two are same, that is symmetrical. So this is symmetrical ether, and what are aliphatic? Number B. And here, okay, number B also. This is also methyl. This is the ethyl. What are aliphatic? Hydrocarbons, right? So though these are different, if these two different, these five types of the ether we call unsymmetrical ether, right? So this symmetrical and unsymmetrical, not only symmetrical and symmetrical, if this one is the the aliphatic, like the carbon chains, right? If here also carbon chain, here also carbon, here also carbon, here also carbon, that's what we call aliphatic. So aliphatic ethers, this is also aliphatic ether because this is the carbon chain, carbon, right? So that types of the ethers, okay, we have another number C. C6H5 oxygen, CH2 and CH3. So here C6H5 is aromatic. This is aromatic and this is aliphatic, right? So if this one is aliphatic, one of them, or one of them is aromatic, okay, no doubt. So these three can be prepared by Williamson synthesis, right? But how can prepare, that is another case, but all these three can be prepared by Williamson synthesis. But the last D, what are aromatic? What are aromatic, right? So if these two are aromatic, so that ethers does not possible to prepare Williamson synthesis. What's the reason? I show you here. See, how do Williamson synthesis write here? See, one of the compound is C6H5, then this one, it should be halogen, let me write X. Plus another one, it should be Na oxygen, so C6H5. For this case, it's no problem, right? Anything we can write. For this problem, we can take it. But for this case, right, this is the haloarine. Let me draw the structure of this one and write this one, alright? So this X is replaced by this sodium, right? So what is the reactions follow? This is the nucleophilic substitution reaction, right? So now in our nucleophilic substitution, haloarines are less reactive, very less reactive. Under the normal condition, this haloarine does not take place. Therefore, this compound, when we choosing this compound, no doubt we can be used. So when we should use this one in this compound, right? If we use this compound, right, that's not any reaction with this compound because the reaction follow the nucleophilic substitution reaction. So therefore, this haloarine is less reactive towards the nucleophile. So there's no reaction takes place. So this product D, I mean this option number D, so not possible for the preparation. So this is option number D. So this must for the questions carry the 1 mark. So you check it your answer with your answer paper. I mean what you written in your answer. So you just analyze yourself. So it's the way how we can examine our answer ourselves. Okay, so I hope you did well in your exam. I just pray to God you just will be fine in your results. Okay, all the best. Okay, thank you very much. See you on the next day.